Good afternoon, Internet. I am Matt Booyak, and in this video we will not be tackling the 44th problem from the Project Euler problem archive. Now, I originally intended to tackle this problem today. Read through the problem description, it seemed quite tame. It's only rated 5% for difficulty. But I have to confess, I have yet to come up with a solution to this problem that is both simple and efficient. I thought I had a solution, wrote it up, and it took about 10 minutes for my workstation to come up with the answer. And that's on modern hardware. This problem is almost 20 years old. Obviously, I was missing something. Just about an hour ago, I did come up with an approach that I think will be efficient, but it's not particularly simple. And there's a little bit more background work I want to do on that before I make a video using that approach. And so for now, instead, we'll be taking a look at this problem. Now, before we get into this, I just want to say, if you took a look at the 44th problem and it seems obvious to you how to solve it, maybe just keep that to yourself for now. Once I upload my video, feel free to tell me in the comments just how dense I've been. But for this problem, we'll be looking at triangular, pentagonal, and hexagonal numbers. Now, triangular numbers have come up on the channel somewhat frequently. The idea is that if you add up the first n natural numbers, 1 plus 2 plus 3 plus 4 plus 5, all the way up to n, you will get the nth triangular number. More conveniently, we have this expression here, so we don't actually have to add up all those numbers. We can just use this formula. And the name for these numbers, triangular, comes from the idea that if you were to arrange some number of items in n rows, with the first row having one item, the second having two, the third row having three, and so on, your items would form a triangular pattern. And I'm assuming that there's a similar inspiration for the names of the pentagonal numbers and the hexagonal numbers. I'm not particularly familiar with those, but we don't need to be. We have these expressions here to help us calculate them. Now, in particular, this problem asks us to find the next number after 40,755 that is triangular, pentagonal, and hexagonal. And the way we're going to do this is we're going to start off with one number of each type. In particular, the 286th triangular number, the 166th pentagonal number, and the 144th hexagonal number. And then we're going to repeatedly find the smallest of the three and toss it out and replace it with the next number of the same type. So let's say, for example, that the 286th triangular number was smaller than the 166th pentagonal number and the 144th hexagonal number. We would take that number, throw it out, and replace it with the 287th triangular number. And we just repeat this process until eventually we have all three numbers will happen to be the same, and that will be our answer. So let's get into it. As usual, we will copy our template directory to make our problem directory, enter our problem directory, and open our main.cpp. Just for convenience, let's make ourselves some little helper functions, one for each of the three types of numbers, so that we don't have to remember those formulas. So we'll say get try, this one I do remember. That's just going to be idx times idx plus 1 over 2. And then we've got get pent. And I believe this one is 3 times index minus 1 over 2. Let me just check that. Yes, n times 3n minus 1 over 2. Then we have n times 2n minus 1 is the hexagonal numbers. Just jotting that down first before I forget. Okay. And let me actually just double check those real quick. It would be a shame if I got those wrong. So we have index times index plus 1 over 2, index times 3 times index minus 1 over 2, and index times 2 index, minus 1, not over 2. And this is why we double check. Okay, so now we can get to writing our solutions. So we're going to have indices I, J, K, and then the numbers tri, pent, and hex. And we're going to say I is equal to, let's bring this back up here, 286. J is going to be equal to 166. And K is going to be equal to 144. Then we'll say tri is equal to get tri of I. Pent is get pent of J. And hex is equal to get pent K. And we're just going to say while tri is not equal to pent, or tri is not equal to hex. Excuse me. Notice that we can convince ourselves that if this condition is false, all 3 numbers must be the same, because the negation of this statement is that tri is equal to pent and tri is equal to hex. And if it's equal to both, all 3 must be the same. Okay, so now we need to find which number of the 3 is the smallest so that we can replace it. So we'll say if tri is less than hex and tri is less than pent, plus plus I, tri is equal to get tri I. Otherwise, we know that tri is not the smallest, so it's either pent or hex. So we'll say if pent is less than hex, then it must be the smallest of the 3. So we'll say plus plus J. Pent equals get pent J. And if neither tri nor pent is the smallest, it must be hex. So then we say plus plus K. Hex equals get hex K. And that should be all we need. Oh, I just happened to notice a fatal mistake. These numbers need to be 64-bit numbers. These numbers are going to get way too big, way too quickly for a standard integer to be adequate. So we need to be sure to do that. And then down here, we'll just say printf. Excuse me. Tri is equal to, or in fact we can say solution is equal to %LD. And any of the 3 numbers will work. We'll use tri. Let's go back to our shell and make and run. And we have a solution. So let's check to see if it's correct. Go down to problem 45. And we see that, in fact, it is. So thank you so much for watching. I hope you'll join me tomorrow for possibly problem number 44 or possibly problem number 46. We'll have to wait and see.